Imagine that you are going to pick up a very heavy box off the floor, like the person shown here on the left side. The person on the left is doing it the correct way. They are bending the knees in order to pick up the box. And this has a very low risk for injury. The person on the right hand side is not bending their knees, and so when they pick up the box and straighten up, the risk of injury is very high. So the problem with the person on the right is that their back muscles are overly stretched. When you take a close look at the sarcomeres in these back muscles, the sarcomere length is too long. It's overly stretched. So the problem with this is that when this person straightens up, it's not possible for the back muscles that are overly stretched to support the back. This is because when the muscle is activated, the back muscle is activated, it cannot develop enough tension to support the back. So the muscle tension is too low and it cannot support the back, and the risk of injury is high. Now let's take a look at the person who is doing it the correct way. When this person bends their knees, their muscles in the back are slightly stretched, and the sarcomere length is just perfect. It's not too stretched, it's not too long, and it's not too short. As a result, when this person straightens up, the muscle tension, when stimulated, is going to be just right. The muscle tension is going to be really high, and as a result, the back muscles are supported, the back is supported, and the risk of injury is very low. Now, I want you to imagine that you're getting ready to do some kind of exercise. You could be going for a jog, or you could be getting ready to dance, or do some kind of strenuous exercise. And let's say that your muscles are not stretched at all. They are overly contracted. You have not stretched before you started your exercise. Here, the sarcomere length is way too short. And this means that when this muscle becomes activated, the muscle tension is too low. And as a result, the movement is not supported as efficiently as you would like. We call this the length-tension relationship. And this is the reason why we carry out stretching exercises before we attempt any kind of strenuous exercise. Now for warm-up exercises. Warm-up exercises greatly enhance our performance. This is because they influence muscle function in a very positive way. Let's take a look at that. Here's a graph with time on the x-axis and muscle tension on the y-axis. Notice how the muscle tension is gradually increasing from left to right. The more warm-up exercises you do, the greater the muscle tension. We call this TREP, this gradual increase in muscle tension, and it has many benefits. For one thing, the muscle is warmed up. This means the temperature of the muscle has increased, and this increases blood supply to the muscle. Once blood flow increases, it brings more oxygen to the muscle. This means more glucose can be broken down to give us more ATP. A muscle that has been activated in this way also has many more action potentials created. And when action potentials are created, more calcium is available. Calcium is available in the synapse, and calcium is available in the sarcoplasm for muscle contraction itself. And like we said earlier, there is a lot more ATP. All of this helps to increase performance. We do this by increasing flexibility, we increase the range of motion, and we reduce the risk of injury and the risk of pain. Now let's take a close look at a muscle twitch. We have time on the x-axis and tension on the y-axis. We start with the latent period when the muscle is being activated, and this will be followed by contraction, muscle contraction. and then the muscle relaxes, and we have the relaxation period, and you go back to the latent period, which is the resting muscle. 1 is latent, 2 is contraction period, and 3 is relaxation period. You can also have a series of muscle twitches, which we see here. What happens if these twitches come in rapid succession? Then we may have a problem. The muscle might go into spasm. So we call this when the muscle contracts but doesn't relax fully and keeps increasing in tension greatly. We call this period incomplete tetanus, which is shown as A. B is complete tetanus, when the muscle completely contracts and cannot relax. This is when we say that you have a muscle cramp or a muscle spasm. When your muscle contracts, the myosin heads must make contact with the actin. For every myosin head that makes contact with the active site on actin, it needs to carry out the power stroke. If you remember, 1 ATP is used for every power stroke. There are many myosin heads in a single myosin molecule. There are many myosin molecules in a single sarcomere. There are many sarcomeres in a single myofibril. There are many myofibrils in a muscle fiber. There are many muscle fibers in a muscle fascicle, and there are many muscle fascicles in a whole muscle. So think about the amount of ATP the muscle needs for a single muscle contraction. So the energy needs of a muscle are staggering, especially when you exercise. So let's say that you're just starting out, you're going to exercise. When you start out, you might have some ATP already available in the sarcoplasm. So this free ATP is used at the beginning of your exercise regimen. Then you keep running. Let's say you're running and you need more ATP. Now you've run out of all your ATP. You have to rely on another molecule called creatine phosphate. Creatine phosphate is already available in the muscle. It provides the phosphate to ADP. ADP is adenosine diphosphate. It picks up that phosphate from creatine phosphate and becomes ATP, which is adenosine triphosphate. So you've got some creatine phosphate. Let's say you run out of that as well because you need lots of ATP. So now your muscle will break down glucose to provide pyruvic acid. This portion is glycolysis and it takes place in the cytosol of the muscle, which means that this is anaerobic as well. There's no oxygen present and you only make a small amount of ATP. You use that ATP for your energy needs. This pyruvic acid also gets converted to lactic acid. That's not a good thing because lactic acid can make your muscles feel sore. And lactic acid causes another problem. It creates oxygen debt. This means you need lots of oxygen to convert all this excess lactic acid in the body to be converted back to pyruvic acid so that pyruvic acid can continue into the aerobic respiration. For the time being, some of the pyruvic acid is still converted to acetyl-CoA and enters the aerobic respiration, and you get energy to complete your exercise. But you still have all this lactic acid in your blood, creating oxygen debt. And that debt can only be repaid when you rest, which is why sufficient sleep is very important to pay off this oxygen debt and feel refreshed so that your muscles can enjoy peak performance. Speaking of peak performance, let's consider world-class athletes for just a moment. Depending upon the type of sport that they excel in, a world-class athlete might have an abundance of one type of muscle fiber over the other. What are these muscle fibers? We have two major muscle fiber types. They are the slow twitch fibers and the fast twitch fibers. Here's a muscle fascicle. These circles shown in the dark pink are the slow twitch fibers, and those that are the light pink are the fast twitch fibers. The fast twitch fibers are abundant in sprinters, basketball players, bodybuilders, and jumpers. What do these athletes have in common? These athletes must carry out intense movements in very short bursts. So this requires fast twitch fibers that can carry out this type of motion. With the slow twitch fibers, those are abundant in marathon runners, swimmers, power walkers, and cyclists. Slow twitch fibers can work for a very long time without getting tired. So endurance is the hallmark of slow twitch fibers. For non-athletes, the distribution of slow and fast fibers tends to be roughly equal. But for a world-class sprinter, for example, they would have 80% fast and 20% slow fibers. The same goes for world-class marathon runners or swimmers. They tend to have 80% slow fibers and 20% fast fibers. Now, with the fast twitch fibers, they rely on anaerobic respiration, and as a result, they don't need that much oxygen. So they rely on fewer capillaries, fewer mitochondria, and they do fatigue easily because they don't produce a whole lot of ATP. The slow fibers, on the other hand, rely heavily on aerobic respiration, which means they need a lot more blood supply. So they are abundantly supplied with capillaries, and they also have a lot more mitochondria to carry out aerobic respiration. And these muscles do not fatigue easily because they make a lot more ATP.